All speakers.
You can play this video first.
Sorry, I can't hear any sound from the video.
It's on live now. Okay, I think it's now live. Okay, good afternoon, good morning, and good evening. Sorry, this. Welcome to this IEEE Powering Summit 23rd. This is the third time of this event, and is now becoming this flagship conference of IEEE young professionals. I'm Gen Li from Technical University of Denmark. I'm actually now in charge of this academic and subcommittee activities in charge of organizing this year's YP track. So today we are very honored to have several distinguished speakers from the industry, from the academia. So we have Dr. Xin Jin from Technical University of Denmark, DTU, and also Dr. Chen from University of Birmingham. We also have Vishwas from US, and he is also a Ph.D. student, and also from Faris. So welcome our speakers and enjoy this today's speech. Now over to you, Faris. You can host and moderate today's event. Okay, over to you.
All right. Am I making myself hearable?
Yes.
Hello? Okay. Thank you, Mr. Chen, for the introduction. My name is Gharbi. I'm a IEEE member in Politics Facts, and mostly I'm graduated as a mechanical engineer. I started the YP experience recently as a representative in the Region 8, and I'm so glad to meet you in this event. I think we should start with, as the plan said, we should start with Miss Dr. Jin. Chen Jin. Am I saying it correctly?
Yeah, that's right.
All right. Yeah, as Miss Chen, Dr. Chen,
So
I
I
should,
can start now.
first of all, I will make a little bit description
Okay.
of your profile, and then you can start. Okay. Just a second. All right. So Dr. Xin Jin has received uh, the Bachelor Engineer degree in Architecture, Environment and Equipment Engineering for China University of Petroleum in 2016. The Master in Science degree in Architecture and Civil Engineering for Harvard University of Technology in 2018, and PhD degree in Architecture and Civil Engineering from City University of Hong Kong in 2022. She is currently working at Technical University of Denmark as a postdoc. Her main research interests include renewable energy storage and power to hydrogen techniques. So, without further ado, Dr. Chen, the floor is yours. You can start.
Share screen. This one. Sorry. So can you see the screen now?
Not yet.
No?
No, not yet. Did
Nothing?
you press present or not?
Yeah, I choose the screen sharing.
All right.
It's coming
Now
up. Yeah, you can start.
Okay. Good. Good afternoon, everyone. My name is Xin Jin, a postdoc at Department of Wind and Energy Systems in Technical University of Denmark. And first of all, thank you so much for giving me this opportunity. And it is my pleasure to introduce myself and my recent research work here. As for my educational background, I will introduce myself briefly. I finished my PhD work at the Department of Architecture and Civil Engineering in City University of Hong Kong in 2022. And my PhD research work was mainly focused on developing multiple renewable energy storage systems for building heating. And I received my master's degree from Gharbi Institute of Technology. And the research was mainly focused on the flow and heat transfer analysis of flue gas using the computational fluid dynamics. And coming towards my expertise and research interests, my research agenda is driven to promote energy conservation and the economic benefits of building energy systems. And my key research has been focused on areas of renewable energy storage technique and energy management systems, particularly in latent heat thermal energy storage technique and techno-economic assessment of the multi renewable energy storage system. And now I will briefly introduce my some recent research work, which was focused on the techno-economic assessment of the multi-renewable energy storage system based on experimental and numerical investigations. Energy storage systems operated with optimized charging and discharging control strategies can make better use of the intermittent renewable power and achieve peak load shifting. Moreover, latent heat thermal energy storage technique using phase change material as a storage medium could achieve higher thermal storage capacity at a nearly constant temperature range, providing great solutions to energy flexibility enhancement for building energy system. And the first objective of this research work is to develop the desired latent heat storage medium for the heat pump. And to better implement the storage technology, we developed latent heat thermal energy storage mediums matching the operation condition of heat pump. We used salt hydrate sodium acetate trihydrate as the base phase change material and employed potassium chloride and urea to modify its phase change behavior, and adding the nucleator and thickener to solve the phase separation and supercooling issues. The thermophysical properties, crystalline phase, and microstructure of the storage medium were characterized using the DSC, XRD, thermocycling, and FGIR tests. More detailed studies were conducted to investigate the practical application performance of the novel phase change material using in the heat pump. And an experimental setup was established to address the feasibility of integrating the latent heat thermal energy storage technique with heat pump for hot water supply and investigate the energy performance of the entire heating system. And the comparative study was carried out to assess the impacts of the flow rate and the supply water temperature on the thermal characteristics of the system regarding the coefficient of performance, power consumption, and the temperature variation of storage medium. And the optimal operating parameters that result in a better energy efficient potential of the entire heating system was further analyzed and discussed. The corresponding thermodynamic modeling of the heating system was established using the Transys coupled with the MATLAB, and the dynamic charging and discharging performance of the assembled storage apparatus and various operation conditions were numerically examined. The implication of integrating the hybrid latent heat thermal energy storage unit with the heat pump to meet the residential hot water demand was assessed. And the optimization study was further conducted to determine the design parameter and identify a desired phase change material that could match the heating system. And the thermal buffering amount and the critical design factors were specified to enhance energy flexibility without sacrificing the main thermal comfort of the end users for achieving less power or expense. And the detailed assessment of the potential heat pump storage configuration was finally carried out to investigate the applicability of various operation strategies for the heating system. And to further promote energy conservation and cost-saving potentials, another renewable energy source, solar energy, was further introduced into the system. And a low-carbon multi-energy system renewable source integration with the developed latent heat thermal energy storage unit was proposed, and an indoor test stand was established, and the feasibility of the multi-renewable energy storage system for building heating was experimentally evaluated. Moreover, the system performance regarding energy efficiency, power consumption, and temperature variation under different working conditions and operation modes was compared. Also, to predict the long-term economic and environmental benefits of the developed system, a simulation platform describing the energy transmission between each component was created, and the practical application of the solar heat pump latent heat thermal energy storage system, concerning the real scenario to supply hot water for the end users regarding dynamic weather conditions and the variable demands of end users, was further evaluated using the simulation platform. And also, we proposed several heating modes and connection modes of this heating system, from the parallel one to the single heating mode. And the design scheme regarding the sizing and operation strategy was further optimized to enlarge energy conservation and economic revenues. And the dynamic life cycle assessment of different system configurations was further compared to achieve an optimal system. And we also worked on some related research projects other than the above-mentioned research work, and there is also a brief introduction of those projects. And for the first one, an experimental test rig was designed and developed to compare the thermal performance of the solar and heat pump latent heat thermal energy storage system, containing different phase change materials with different phase change behaviors as the thermal energy storage mediums, and assess the effects of the phase change area, such as the phase change temperature and enthalpy on the thermal efficiency and energy consumption of the heating system. And we also prepared and developed the thermal stable phase change material for space heating application, and the thermal comfort level of the radiant flow heating system with different layer structures was evaluated. Also, we have expanded on the idea of utilizing the multi-renewable energy storage system to formulate net zero energy communities, an interactive energy sharing and management system involving multiple renewable energy storage system to formulate net zero energy communities, and with electrical and thermal energy storage, flexible demand-side controls and predicted information exchange was developed for a neighborhood level. And the final project is about a dual latent heat thermal energy storage tank. And we proposed different charging strategies to achieve a more efficient operation for the heat pump. And an experimental study was conducted to investigate the effects of the several different charging strategies on the heating collection efficiency of the system. And the dynamic charging was realized based on the automatic control using the PLC. And here are some selected publications in recent years. And that's all. Thank you so much for your attention.
Hello? Can you hear me?
Yeah, I can.
You should share your screen again, please.
Okay. Screen. Window. No, this one. So can you see now? I share the screen. Yeah.
Yeah, now it's working.
Hi, Ferris. I think Dr. Xin finished her presentation, so you can move on to the next speaker.
Okay, thank you very much, Ms. Chen, for presentation. I don't know if it's possible to ask question or we should move on.
And now, no, from this platform, this comments is from this YouTube, so
Okay.
we cannot collect the comments from them. No. You can move on to the next stage,
All
and
right.
we can collect the comments and questions at the end.
All right. So moving on to our next speaker, Mr. Nansha. Just I will share with you a little brief description about him. Dr. Nanshan received a Bachelor Engineering degree in Electrical Engineering from the Hong University of Science and Technology in Wuhan, China in 2012, and his Master of Science degree and his Ph.D. degree in Electrical Power System from the University of Birmingham, UK in 2018 and 2022, respectively. Okay. He currently with the School of Engineering, University of Birmingham. His main research interests include HVDC modeling and control, power system operation and protection, and power system restoration plan. Dr. Mention is currently the communication officer and of the IEEE PAS UK and I chapter. He also acts as a secretary and treasurer of the CGRE UK NGM and supporter of CGR UK V4 Study Committee. Without further ado, Sir, the floor is yours. You can start.
Thank you very much. Can you hear me, Ferris? Can you hear me?
Yes.
I can hear you.
Okay, great. Thank you very much for your kind introduction. Dr. Gharbi, can you help me to share the screen, please?
Yes, I'm sharing screen. So, Carlos, so please share the screen from mine. Yes, it's coming.
Okay, great. Thank you very much for Dr. Gharbi inviting me into this great opportunity. The IEEE PS Young Professional Powering the Future Summit 2023. So today I'm going to give a talk on the emerging hybrid HVDC technologies, which is an overview. So next page, please. So yeah, this is my brief introduction, which has been mostly introduced by Mr. Ferris. So I want to highlight that before I became the communications officer of the IEEE PS UK and I chapter, I have been taking the role of the chair and the vice chair of the IEEE student branch, including PES student branch chapter and the University of Birmingham for more than 3 years. So I really appreciate this great opportunity given by Dr. Gharbi to make contribution to the IEEE PES, especially in terms of the young professionals. Thank you. So next page, please. So today's topic will cover the following 5 parts. So it's mainly divided into 2 parts. The first 4 topics belong to the first part, which is an overview about the hybrid HVDC. The second part will be the 5 bullet point case study by using proposed flexible LCC HVDC, which is one of the hybrid HVDC technology, to demonstrate the economic performance as well as the technical performance. Next page, please. So firstly, we'll talk about what is hybrid HVDC. So hybrid HVDC can be regarded as a combination of a conventional HVDC, which is thyristor-based. For example, line commutated converter-based high HVDC, which is shortened for LCC HVDC, and also capacitor commutated converter-based HVDC, CCC HVDC. And another major component of the hybrid HVDC is new HVDC, which is IGBT-based HVDC. It has other names, for example, HVDC Lite or HVDC Plus, named by different producers all over the world. So it includes the voltage source converter-based HVDC, which is VSC HVDC, and also MMC HVDC, which stands for modular multi-level converter-based HVDC. So motivations why we propose the HVDC, the hybrid form. So firstly, we would like to overcome the problems caused by the semi-controlled semiconductor, which is thyristor-based HVDC. First one, combination failure. Second one, an inability to control active power and reactive power independently. Third one, inability to black start. Second aspect is to overcome the problem caused by the full controlled semiconductor-based HVDC. First one will be high converter power loss, including conducting loss and switching loss. And the second one will be low voltage level, resulting in low active power transmission. Third one will be high cost. Next page, please. So next, I will introduce several types of the hybrid HVDC topologies, which covers nearly all of the topologies right now all over the world. Next page, please. So I will introduce 5 types of the hybrid HVDC. The first one will be the hybrid in-field HVDC. It has basically several forms. For example, 2 different types of HVDC are built from the same receiving end, from the same sending end to the same receiving end, or the 2 HVDC links can be from different sending ends. The second HVDC hybrid HVDC type is hybrid end HVDC. So which means that it has LCC HVDC at the sending end and VSC HVDC inverter at the receiving end. And it also can be applied into bipolar HVDC rather than only monopolar HVDC. It also can be extended in terms of multiple sending end or multiple receiving end. The third type of the hybrid HVDC will be hybrid pole HVDC. It's majorly applied into bipolar HVDC. So for example, one pole is utilizing the LCC HVDC, another pole is using the VSC HVDC or MMC HVDC. The next page, please. The fourth topology of the hybrid HVDC is hybrid valve group HVDC or hybrid valve HVDC. It means that no matter it's a bipolar or monopolar HVDC, each pole will be composed by 2 technologies. For example, it is a LCC and a VSC cascaded pole. For example, the 4.A. It's a 2-ended monopolar hybrid valve group HVDC. It can also be extended to bipolar, which means that it can both of the LCC and VSC technologies can be applied into both poles. The final topologies of the hybrid HVDC is other ones. For example, flexible LCC HVDC based on controllable capacitors. The basic idea is that in terms of the LCC HVDC, the conventional one, the University of Birmingham proposed the idea of adding the fully controllable capacitor into the inverter station between the inverter valve groups and the transformer to realize the controllable combination voltage to eliminate the combination failure. And the second one will be the controllable LCC HVDC based on IGBT. So basically, you can see that the inverter side of the LCC HVDC is replaced by the valves composed by the thyristor diode and IGBT based valve. Okay, next page, please. So next, I will introduce several best applications of hybrid HVDC, which has been realized and installed all over the world. The first one will be the hybrid in-phase HVDC. So one of the typical typical application is Loxi back-to-back HVDC project. I have put some references here. If you are interested, you can look into more details. So it's basically it consists of two LCC HVDC, 1 gigawatt each at the voltage level of 160 kilowatt, and also one MSC HVDC with the transferring capacity of 1 gigawatt with the voltage level of 350 kilowatt. The second one is hybrid end HVDC. The typical application is Kunliu ultra high HVDC project with the voltage level of plus minus 800 kV with the total transfer capability of 8 gigawatt. Next page, please. The third one will be hybrid pole HVDC. It is applied into the Skagerrak 3 and 4 link project. So it consists of the bipolar HVDC consists of the two technologies, one LCC with the voltage level of 350 kV and 500 megawatt, and one link of VS HVDC with 500 kV rated voltage and 700 megawatt transferring capability. And the fourth one is about the practice of the hybrid valve group HVDC. The best practice is the Baihetan Jiangsu ultra high HVDC project, also with the plus minus 800 kV and 8 gigawatt capability. You can see that from the topology. You can see the inverter side of the HVDC link consists of LCC HVDC, a 12 pulse LCC HVDC cascaded by 3 VS HVDC in parallel. So next page, please. The final hybrid HVDC is the application is the flexible LCC HVDC prototype. So it's basically idea is from the flexible HVDC LCC HVDC I have introduced in my last page, and it has been installed. It has been applied into a prototype project, which has been reviewed by industry experts. Okay, next page, please. So basically, I will give a summary of the advantages and also disadvantages of hybrid HVDC. So basically, I will talk about the 5 aspects for including the communication failure elimination ability, and also the ability of active power and reactive power control capability, and also whether it can black start, and what about the efficiency of the converter station, and also how about the economic performance, for example, whether it has low cost. So basically, from the comparison, you can find that the flexible LCC HVDC proposed by Birmingham can have the benefit of eliminating conversion failure, has low cost and high converter station efficiency. And then the next part I will introduce, I will go into some more details about the economic performance of the flexible LCC HVDC. Next page, please. So from the comparison, we can find that the future challenges in research and also practical applications will be fast power flow reverse, reactive power compensation, capacitor voltage balance strategies, AC system strength at the inverter side, system restoration strategy, and also interactions between the control systems of different HVDC topologies. Okay, next page, please, will be the final part. So I will give a case study to look into more details about the economic performance of the flexible LCC HVDC. So the reason why we propose, the motivation we propose this economic analysis is that the previous research or topologies can only mitigate itself competition failure rather than totally eliminate the competition failure. However, the proposed flexible LCC HVDC can eliminate the competition failure, which is a major problems existing in the conventional LCC HVDC systems. And also, there's a lack of economic analysis comparing the cost of different LCC HVDC schemes. And so we compare four models. The first one will be the conventional LCC HVDC. The second one is the proposed controllable capacitor-based flexible LCC HVDC, which is shortened for CC LCC HVDC. The third one is an improved one, which is AC filterless controllable capacitor-based flexible LCC HVDC, ACFL CC LCC HVDC. The final one is proposed in this paper, in paper 7, which is the improved AC filterless controllable capacitor-based LCC HVDC. So from the topology at the right side, you can see that for the topology 2, the flexible LCC HVDC, we insert a fully controllable capacitor modules between the inverter valves and the inverter transformer. And based on this topology, in topology 3, we remove the AC filters on the inverter bus and put some parallel capacitors between the controllable capacitors and the inverter transformer to realize the reactive power compensation as well as the harmonics filtering. And based on this, we realized that since there's a very limited harmonics going through this inverter transformer, so basically this LCC HVDC inverter transformer can be replaced by those which is utilized in VS HVDC, which needs less capability redundancy for harmonics, so which can further reduce the cost. So this is the 4 topologies which will be compared in the following slides. So the method we are going to use is the life cycle cost analysis method. So basically, it is shortened for life cycle cost, which is LCC, but to distinguish between the LCC line commutated converter and our life cycle cost, we just shorten the life cycle cost analysis with LCCA method. So it consists of 5 parts: CI, CO, CM, CFF, and CD, where CI is the initial investment cost at the beginning stage. And CO means the operation cost, CM is maintenance cost, CFF is failure and fault cost, CD is disposal cost, which is normally negative. And we proposed 4 scenarios to compare the proposed 4 topologies. The first one will be a standard 500 kV, 1000 megawatt monopole LCC HVDC project inverter station. So basically, the difference between the flexible LCC HVDC and the conventional HVDC is the inverter station configuration. So we compare the inverter station life cycle cost. From the right side figure, the first figure is the investment cost comparison. It can be seen that the initial topology, which is the original flexible LCD HVDC, will increase the investment cost by 26%. But with the topology 3 and topology 4, we can see that the investment cost can be reduced by 3% and 12% respectively. And for the life cycle cost comparison, it can be seen that all of the topology proposed by us in terms of the topology 2, 3, and 4 have no CFF in terms of the combination failure. And also the topology 4 can reduce the life cycle cost by 7%. Next page, please. The second scenario and the third scenario will be shown here. The second one will be about the comparisons of considering different discount rates. So with the increase in discount rate, it can be seen that compared with the topology 1, which is the conventional HVDC, all of the proposed LCD HVDC can reduce the life cycle cost further. And for the scenario 3, comparisons considering the practical fault impedance, why we propose that is because that from the studies by other researchers, we found that the average fault impedance from the fault point to the ground will be not 0, but it's normally around several ohms. So basically, our previous comparisons are based on zero ohm impedance of fault of 0 ohm fault impedance, but here we put the side data on the comparison. So from this, we can find that the proposed topology 3 and the topology 4 can reduce the life cycle cost by 10% and 19% respectively. Next page, please. So this page is the final scenario, which is the comparisons considering reliability of the flexible LCD HVDC technologies, where we consider 8% of the redundancy rate. Additionally, we also put the conventional CCC HVDC into the comparison, which is topology 5. So basically, from the investment cost comparison, it can be seen that the proposed topologies 3 and 4 can reduce the investment cost by 9% and 18% respectively, which is much larger than the CCC HVDC. And in terms of the life cycle cost, the topologies 3 and 4 can not only reduce the cost, but also can avoid the cost caused by the combination failure. Okay, the next page, please. So conclusion. So all the hybrid HVDC topologies have combination failure risks, except the flexible LCD HVDC proposed by the University of Birmingham. And life cycle cost comparison considering the zero impedance AC faults, the life cycle cost of the inverter station, the CC LCC HVDC, AC failureless CC LCC HVDC, and the improved one are 142% and 102% and 93% respectively of that of the conventional LCD HVDC. And also the topology 3 and topology 4 can reduce the cost of the inverter station by up to 9 and 18% respectively, considering the practical fault impedance and maintaining the reliability, while they can still have super performance in eliminating combination failures, reducing the harmonics, and avoiding related risks. So that's all for my presentation today. Thank you very much for your time.
For your presentation. Moving on to our next speaker, Mr. Vishwas. Powar, am I pronouncing it correctly?
Yes, that's correct.
All right. So Mr. Vishwas is a PhD candidate in electrical and computer engineering at Clemson University in the US. He received his Bachelor of Engineering from University of Mumbai, India, and his Master of Science in Intelligent Systems from Clemson University in the US. As a PhD candidate, his research is focused on power flow control and optimization for the next generation of the general networks. His research includes utility scale PV for farm sizing, standalone and grid-tied battery energy storage systems, and intelligent fast charging for electrical vehicles. He has published over 20 research papers, a book chapter, and two trade journal articles. His research was selected as the top 10 finalists for CEGRA, a U.S. National Communities Next Generation Paper Competition in 2021. He was awarded the 2023 Outstanding Graduate Teaching Assistant and Outstanding Graduate Student Service Award by the Holcomb Department of Electrical and Computer Engineering at Clemson University. Mr. Vishwas is the chair of IEEE Power and Energy Society's student branch chapter at Clemson University, and he is the chair of the IEEE Non-Professional Affinity Group in the Birmingham section Region 3. He is actively involved in his IEEE Region 3 and serves as the member and newsletter editor for the IEEE student activity community. He's also served as an ambassador for IEEE Peers Day 2023. Mr. Vishwas is inducted into the IEEE ETA Kappa EU and PHI Kappa PHI Honor Society. He aims to be an industry fellow in the sustainable power sector. Okay, so Mr. Vishwas, the floor is yours.
Thank you so much. You can hear me okay, right?
Yes.
Okay. Thank you so much, Faris and Dr. Chen. That was a good introduction, so I appreciate that. I'm going to try and share my screen. Just give me a minute. Do that. Can you all see my screen? Is my screen visible?
Not yet.
Not yet? Okay.
Hi, Cagnas. Are you there? Can you share the screen?
Let me try and share the screen once again. Okay, can you see my screen now?
No, not yet.
Okay, I think I get a processing symbol, so maybe it's just.
I think when you share it, you can see it at the bottom with your
Okay.
profile. There is a small box there.
Hmm. Hmm. Sorry, give me 1 minute. I don't think this is allowing me to share my screen. Okay, I'm trying to upload my presentation here, so probably we can share it through that. Yeah, before, like, as we wait, I wanted to thank Dr. Jin and Dr. Chen because they did a great work going before me. Always being the last presentation is challenging, but I'll try to give you a brief overview, and without going into too much details, I would like to blend a little bit about my journey in IEEE, the motivations I received, the feedback I received from mentors in IEEE, and how I have applied that in my research. So I would like to do that through the presentation. Okay. Okay, you can see it now, right?
Yes, yes, please.
Okay, great. All right. I'll try to do justice to the time. I know we have 10 minutes left for the session, but good morning, good evening, and good afternoon, everyone, from wherever you're joining. My name is Vishwas Powar. I'm a PhD candidate at Clemson University, South Carolina, USA. I'm also involved in the young professionals since some time now. And the talk for today would be about end to end sustainable power networks. Uh, the outline is such where I'll just talk about my journey in IEEE. And I would like to draw attention back to sustainable energy. I know that's the theme for our session today, being sustainable, powering the sustainable future. But let's revise the definition of what is sustainable, and then I'll dive deeper into my research here at Clemson University, and then give you some conclusions that I feel the world is heading in the next directions. So let's get started. My journey here in IEEE started as an undergraduate student when I was back in India. So in 2012, I learned about IEEE, and I started an IEEE student branch in my college in Mumbai. And I was the chair at that time. I didn't know that involvement 10 years or 11 years ago would get me here to this place. So since 2012, I've been involved in IEEE as a volunteer. uh, Little did I know that after I graduate, the company that I invite for a talk at our university gave me a full-time job. Although it was not in power systems, it was in robotics and automation. So I worked for a year in India in the field of robotics and automation before starting my master's journey in 2016 here in Clemson University. Again, my master's was in embedded systems and industrial IoT, I would say, and that was in 2016. 2019, I started my PhD. Moving again from embedded systems to sustainable power systems was my PhD. Today, 2022, 2023, I'm actively involved as different roles in IEEE. And looking back at this journey, I've always learned valuable lessons, valuable feedback, so much information, and the ability of people to help each other is tremendous in this organization. Given my background, I've dabbled into robotics, embedded systems, and now power systems. So I would like to bring insights from all those three sections and present today in front of you all. So according to my analysis, I think the next lessons that we have in power systems are based on these four aspects, which is climate, capacity, cost, and control. So essentially, the 4C approach is going to lead to a difference in paradigm shift in all the sectors of the power grid, right? From generation to transmission to distribution to markets. And the end goal would be to essentially provide reliability, resiliency, and robust power network. For my talk today, I've concluded that all of these aspects, which is the 4C and the 3R aspect, can be met with photovoltaics and storage and wind, which is essentially sustainable, ubiquitous, and nearly free. And the acronym again comes down to SUN. So moving on, we have an immediate urgent climate need, and you can see the two figures here, which says that 2022-2023 was one of the warmest days or one of the warmest years on the planet Earth, and this is the 6th time in a row. These are both references from the NOAA, and you can see the rise in temperature. The entire planet is risen, I think, at least 1 degree, and if we don't curb this, it's going to lead to a lot of challenges. The reason for the increase in temperatures, or the global climate urgency, we need to get away from fossil fuel based generation. And essentially, other than the climate urgency, to ensure a global economic growth, to maintain energy parity, and also to reduce geopolitical tensions, moving away from fossil fuels is the need for the hour. Here is just a graph depicting different oil prices when different key events or world events occurred. So you can see the fluctuating oil prices when any event, a geopolitical event occurs, which essentially creates more stress on the grid, increases the prices for electricity, and in the end consumer has to bear all of these effects. So sustainable and green electricity, right? So I would like to direct your attention to this picture here, which says solar energy is the most abundant source. You can see it's 23,000 terawatt hours a year per year, and no other source can compete with it. Another aspect that people always say is solar is abundant, but how about the per capita solar generation? So the graph on the right shows you the abundant availability of solar per capita with different geographical regions. The regions in green have a lower solar, but we have wind energy that essentially supplements the solar energy, and that is what is shown in these two graphs. So wind plus solar can essentially meet the sustainable green electricity needs of the future. The last picture here, the third most slide here, is essentially a world map which indicates that Denmark is one of the European countries which has about 50% of electricity needs met by just solar and wind energy. So this is a challenging and interesting time to note all of these changes in the grid, moving from inertial systems of synchronous generations to incorporate distributive solar and wind energy in the system. Another important aspect of sustainable energy, which is often ignored, is the use of water and carbon emissions. So there exists a sustainable water energy carbon nexus. Essentially, water is needed for electricity generation, and vice versa. Energy or electricity is needed for transporting water, and both of these lead to a nexus, which is also including of carbon. The table on the right essentially lists different sources of energy generation based on their water usage per megawatt hour. And you can clearly see photovoltaics and wind have the lowest usage of water as compared to other different generating sources. The next important sustainable paradigm is land use, right? We have heard that solar panels need a lot of land. Essentially, that depends on area to area, which is location specific, and it also depends on the efficiencies of your different solar panels. So both the figures here, essentially the key takeaway is if we have in surface area equal to Spain, the area of Spain, with only 20% efficient solar PV panels, that is enough to power the entire world. The challenge, however, comes in infrastructure, storage, right? Because we know the sun doesn't shine 24/7, the wind doesn't blow 24/7, but together, wind and solar, along with storage, can supply essentially the entire sustainable electricity for the next generation. Here is another example which demonstrates if land is an issue, there are floating solar panels in Europe, which has been actually done recently. So the area of land, the usage of water, and essentially the carbon emissions. So all these three tie up and make solar, wind, and storage to be the source for a sustainable green electricity. Now, with clean electricity, there's a difference between green and clean, right? And I think as we are moving towards a sustainable infrastructure, we should focus more on green electricity rather than clean electricity. This graph here is just indication of different deaths and greenhouse gas emissions from various sources of electricity. And again, at the bottom, you can see solar and wind, essentially indicating that they are the safest and the cleanest sources of electricity. So there is no question, no doubt that essentially solar and wind are going to dominate the next decade of sustainable generation. Now, coming back to the 4C approach, cost is another important aspect, right? If the cost of the generation is not sufficient, it cannot sustain in the long-term infrastructure. So the graphs here, essentially the first two graphs are indicating the decrease in solar and wind costs. And again, this is utility scale LCOE costs. And you can see the fossil fuel cost range is well beyond the cost of solar. So the current cost is almost 4 cents per kilowatt hour. And this is essentially US dollar cost. But you can see the second graph here showing you that solar prices nearly declined 89% in the past 10 years. And the last graph is showing you the increase in capacity. So within the last 10 years, the newer capacity generations has increased by 118% for PV installation plants. So again, going back to the 4C approach, it's the cost, the capacity, and essentially the important aspect is the storage, right? Because we all know storage is going to be important with respect to solar and wind. Two important graphs here that I want to point your attention to is based on different use cases, the cost of storage is also declining. And then on the right-hand side, based on different durations of storage, the cost will also decline. So this is one of our work on the right-hand side, which we use data from NREL and try to predict how much if we increase the cost of how much if we increase the duration of storage will the costs go down. And essentially you can see increasing the duration of storage is going to increase the cost, or sorry, is going to decrease the cost and essentially make it really viable to plug in your solar plants with co-located battery storage. Nowadays, most of our utility scale solar plants have an issue of capacity factor. The solution is right in front of your screen. Having co-located energy storage can increase the capacity factor and also provide more reliability, resiliency, and robust infrastructure. These are just graphs. In the interest of time, I'll skip this, but essentially it's showing California increasing their storage capacity, and then Australia, which was dominated by pumped hydro storage, that is now being overtaken by battery or lithium battery storage capacity. Now, microgrids, another important topic that we have learned just yesterday. We had a session on AI in microgrids, and as you can see, the primary focus that I wanted to point here is in terms of EV charging. We all talk about microgrids, and there are a bunch of aspects in them. You can have modeling, you can have different ways of integrating your solar systems. Newer microgrids in terms of DC microgrids are emerging. Most of the storage facilities, and then the power management. But all of these are tied up to this load, which is called as EV charging load. And then the graph on the right, we had another talk yesterday from Siemens, where we actually saw this, why is it needed, that EV charging is going to affect the feeder voltages, the feeder loads, it's going to affect substations, and that will need a total upscale of these technologies. Another aspect that people usually don't look at is fast charging and highway charging. So this was a study done by the National Grid, which essentially said that if you have fast charging and interconnects of transmission would be necessary, because they will essentially consume power as large as a small town, as large as a big industrial area, in the range anywhere from 10 megawatts to 50 megawatts peak power. So the distribution grid needs to incorporate some transmission interconnects when we talk about EV charging, fast charging, and scale at which will be needed to scale these things up. I won't go back into all of the issues with the power grid, but rather I want to focus more on the solutions of it. In the interest of time, this was one of the research works that we completed. I will skip mostly the equations and explanations, but what we are trying to do is trying to introduce an end-to-end solution for EV charging in this paper, and those solutions are based on DC to DC systems. And these systems can be implemented for the growing EV load. For already existing AC infrastructure, you do not need to disturb them. For the growing EV charging load, you can have a local combination of LVDC buses to charge the system. You have an MVDC distribution. The transmission should be HVDC transmission with a minor tweak to the converter station. And we heard Dr. Chen just talk about his LCC hybrid approach of converter station. I'll just introduce this DC to DC converter stations. And essentially, we saw 25% power savings if we do an end-to-end systems level HVDC, MVDC, and local DC grids for EV charging. We already heard the advantages of HVDC by my previous speaker, so I would like to skip this slide in the interest of time, but essentially the key takeaways are HVDC systems have lower losses, have narrower right of way, so less construction required, and also the cost, essentially the cost of EV or HVDC systems comes from their converter stations. And the graph on the right-hand side, bottom right-hand side, we have all seen this graph. It's basically the break-even distance, but the break-even distance comes into picture because of the costs, right? And the cost of HVDC comes majoritarily from the converter stations. Going back to our EV DC to DC end-to-end system, This is a medium voltage distribution grid which was proposed. Again, I'll try to keep it really brief and overview. Essentially, what we did is we had 3 different types of charging evaluated. We had passenger EV charging, we had medium duty fleet charging, and essentially also heavy duty fleet like tractor trailers and 18-wheeler trucks. Essentially, what was proposed is a Power Electronics, a modular SiC based DC to DC converter. And the bottom line was the same existing cables can be used for MVDC transmission, and no major upgrades are necessary. I'll encourage everyone, if they're interested, to read the paper. It's published there. So I'll move on quickly to the HVDC approach. On the left-hand side, you can see different aspects of HVDC, which was covered by length by Dr. Chen. On the right-hand side, what we are trying to propose is essentially all the HVDC systems have internal conversion stages, and they convert from AC to DC, and then again back from DC to AC at the receiving end. The conversion stages here lead to a lot of losses, and essentially the need for developing DC to DC converters, essentially with HVDC systems, point-to-point HVDC, essentially having both ends of DC will significantly reduce the losses. And here is the approach for an end-to-end system. So essentially, for all the newer loads, it can be EV charging, it can be residential loads from microgrids or houses, it can be manufacturing plants like cement manufacturing, or also desalination plants. So all different loads can be internally connected via LVDC buses, got over to the MVDC distribution stage, and then implement HVDC transmission for an end-to-end DC approach. Wherever possible, wherever we have area, we can have local solar, local farms based on Thomas Edison's principle, and essentially create this DC to DC system. However, of course, there are challenges, right? So the research and development need is in terms of power electronics, in terms of DC to DC circuit breakers. We need to have more converter stations, advances in those. We need to have power flow controllers, again, the DC to DC power flow controllers. So essentially, this is an evolving topic, and we have a lot of research needs, but essentially it's a potential solution because it has most lowest losses, and again, it is sustainable, which is the title of the talk. I will skip this slide for the interest of time. And this role of storage is really important. And essentially, we just saw Dr. Jin today talk about her storage journey. Adding on to that, the idea of storage needs to evolve. Currently, storage systems are only considered in comparison with the gas peaker plants for 4 hours of storage. Essentially, we saw the duck curve yesterday that Dr. Julio presented, the California duck curve, and essentially the increase in ramping rate needs either gas plants or storage, and that's where the 4 hours of storage comes into picture. But if we want to implement sustainable infrastructure, we need to think about longer durations of storage. So energy-based storage systems of greater than 8 to 16 hours. And different technologies can come into picture. We have heard about hydrogen storage. We have heard about airflow batteries. But essentially, the underlying concept should be all of those should be green and sustainable. And scale deployments should be possible. Large-scale deployments should be possible. As of now, lithium ion has that potential for large-scale distribution and deployments for storage. All right. So I'm going to conclude and wrapping up the entire conversation for today. These are the 5 major trends that we are going to see in the next few decades. And as we want to innovate climate solutions and sustainable future, definitely COVID pandemic is going to lead to medical research. We are in the phase of sustainable energy transition and digitization. The role of artificial intelligence is going to be the next important aspect. Water is important, and water conservation is again going to dominate for the next few decades, and also different interconnected systems, communications, autonomous vehicles will also dominate. I would like to leave you all with the YP mantra, which is essentially we need to move the needle, and YPs or young professionals directly fit into this because we can see the change, we can partake in the change, and we can bring forth the transition towards that change. In the end, I want to leave you with this picture of the future electricity grid, and it will be the 6D drivers of the future power grid. They will definitely have more direct current, which is DC interconnects. It's going to be decentralized, decarbonized with the help of dynamic control, democratized, which essentially means affordable power for all, and definitely digitized. That's my time. Thank you so much.
Okay, thank you very much, Vishwas. It's a very great presentation. I think we are going to the end of today's session. Before we close today's event, first of all, let me present my screen because we prepare some. Let me check. Yes. Cactus, please present my screen. Yes. So we need to give these big thanks to our speakers today. First of all, Dr. Xin Jin from DTU, Denmark. And then Mr. Ferris. And then the Dr. Chen from UK. And also Vishwas from the US. Many thanks. Without your support, we cannot have a great event today. And let's close today's event. We can see all of you guys in next year. Thank you very much. Bye-bye.
Thank you. Bye-bye.
Bye-bye.